First of all, I'd like to thank the organizer for giving me the opportunity to talk here. So this is the third quantum subject to you. And somehow the idea is, of course, that I like to somehow explain the relation between mathematics of tensors and the physics of entanglement. And actually, we are talking exactly the same things. And compared to the two previous talks, my talk is very basic. Partially because originally somehow Rekhen invited me, I thought I could be the only physicist here, so I try to be very somehow take this opportunity to somehow connect what we are doing in physics to the expert. And as a matter of fact, as you can see soon, I've been working on some geometric aspect of the entanglement. And I was contacted several times by the expert in algebraic geometry or invariant theory, but I never had the chance to somehow meet meet in person. So I like to take this opportunity to somehow convey and connect the ideas here. So the first subject is a pretty much similar subject to the previous two talks, but I put more emphasis on the geometric aspect. And you might expect I'm going to teach you quantum mechanics, but you are going to be wrong because I come here to learn quantum mechanics from you because I'm going to say quantum mechanics, or at least the classification of the entanglement, is nothing but algebraic geometry, which you know much better than me. So I learn from you about quantum mechanics in part 1, sorry. And of the part 2, I briefly mentioned the complexity aspect. So in the first day, we saw a lot of property, like people talk about the tensor rank, border ranks. And you can find that these quantities are actually important physically in the sense that they characterize the resource quality if you try to use such. For example, the tensor rank is one of the measures for the amount of entanglement, and this characterizes how useful it is if you use for quantum computation. So this is what I briefly talk about the second part. So the first thing is about the essential connection to the algebraic geometry. And as I mentioned, please feel free to interact with me if you have any questions, because this is my purpose to connect the idea to you. So I start with the stochastic LOCC, which you had already twice today. So essentially same things. And if I a little bit complement the idea, so we like to define equivalence class of the entanglement, or at least somehow the pure states. Okay. And the idea is if somehow they are connected by the invertible operation, which are given by the special linear group, acting locally in this way, then you could expect they have essentially similar resource quality if you use such states for quantum information processing. There are a lot of applications which I don't explain, but they like for teleportation, secret sharing, or quantum computation. So the entanglement is resource. So what we like to do is basically characterize. And first step is define equivalence class. The strict definition could be the so-called LOCC because you care about the probability of success in information processing. But they often somehow, as somehow they start, you might think, well, I don't care about the probability because they are related by the invertible. So if you succeed this one, there's some chance you succeed using the psi prime. Okay. So this is how we define the equivalence under SLOCC. And usually somehow physicists talks about the Hilbert space in this form, but what we actually mean is the rays in Hilbert space. The reason is somehow the overall complex factor doesn't affect any probability in physics, so that what we are really talking is the essential ray phrased differently. We are talking about the complex projective subspace. So the basic dimension is this total dimension minus 1. And then probably if somehow to phrase the question up to this moment, the SLOCC classification is nothing but the classification of the orbits under this the local the special linear group actions in the complex projective subspace, complex the projective space. At this moment, probably you know better than me what we can do. But let me start with the Bipartite case, meaning that the, what if we just apply this strategy in the matrix? So for the case of the matrix, we have the two indices by I sub 1 and I sub 2. And if you can apply each parties, what usually called Alice and Bob, under somehow the SLOCC actions, this means that essentially if you have this the action group action Z, it corresponds to the matrix transformation. M1 is acting from left because it acts on the first index, and M2 is acting from the right because it acts on here. And this is nothing but the singular value decompositions. So that is why if you can apply this the SLOCC, namely this the M1 and M2s are invertible, the special linear operator, then you realize what is invariant. So the invariant is simply rank of this matrix. This is the only thing you cannot change. So the equivalence class are characterized by the just rank here. And usually, physics is somehow write down the right diagram. But for convenience, I draw the more geometric picture on the left. So this is the picture probably you prefer. So the whole space is given by the complex project space of dimension k squared minus 1 in this case. And we have the lot of closure as I elaborate soon, and they are characterized by the rank. Okay, so the whole space is the rank equal or less than k, and the next is of course rank is the equal or less than k minus 1, blah blah blah, and the bottom one is just the we call the product, or you may call the simple tensor or pure tensor here. So the first thing is we characterize equivalent classes, in this case k classes, and then in physics we are interested in the relations, and we can show that this rank is non-increasing under LOCC, meaning that you cannot create the higher state from the lower states because the entanglement is just consumed. So there is only somehow the non-invertible possibility. So you can somehow degrade or consume entanglement from the upper level to the lower, but not other way around. Phrased differently, if you apply the non-invertible G action here, you can only somehow reduce the number of the rank, which you can easily see for the case of the matrices. And if we take the geometric understanding, then this is nothing but the whole space is, as I said, a complex projective space. And the bottom one, the middle one, corresponds to the rank 1 tensor, is the so-called Segre variety. We call the product states or separable state, meaning that they are not correlated at all. And there are a lot of somehow intermediate closures, and they are essentially related to the second variety.
Yeah. The definition of maximally entangled is just in the talk of this morning that you can trace and get the identity in all possible.
Okay, I will comment that actually for the case of the bipartite entanglement, as you notice, there are, you could consider how you could define maximally entangled. And what we did is we somehow, in this case, we have only 9 types. Although, of course, we have a lot of states inside of the class. But we have only 9 kinds. And you call the highest weight class as a maximally entangled state. I mean, it comes with a lot of somehow states, because somehow it goes everywhere, but the other states cannot come here. So usually somehow the definition of the maximally entangled state comes from the operational possibility. And
just because it's the highest of the 9 in this. But there are 9 for every k. So I don't know. No. I don't understand.
So
the top orbit closure is the maximally entangled one.
Yeah, so my definition is different from the Gerard definition.
You said that there are 9.
I have no idea what it means.
Maybe I misunderstood the...
Do I need more clarification?
No, now it's clear.
Okay, yeah. So in particular, the reason somehow people might define the maximally entangled set from the spectrum of the local density operator, not the total one, is if you somehow consider the state inside of this one. So as far as somehow rank is full rank, all states are included here. But if you consider this equal weighted state is most powerful in the sense that this state has kind of the best probability if you really care about the probability inside the class. Okay, some states may have the better performance, although all are somehow connected by the group actions. And that is why when all terms are equally weighted, phrased differently, the local density operator is identity, it is preferred the representative state in the class. So this is, so his definition is a little bit narrower than the I'm using here.
Does this have to do with this business of this critical states that was?
No.
So how do you distinguish which one of these has the best performance within the class?
So in our case, you have to think the SLOCC is the coarse-grained characterization. So if you care about the probability, you have to introduce different equivalence class.
Okay.
So usually people might consider local unitary equivalence, and you have to compare somehow the phasor somehow this direction. Sometimes in one direction is probability 1, but the other maybe somehow works only probabilistically. And you can really somehow compute which one is, has the best somehow the performance. But here somehow what I'm saying is we are doing under the SLOCC we are doing the coarse-grained classification, and we have only 9 kinds of entanglement here.
So just remark, so it's because you don't take unitary transformation, so therefore maximum entangled in Gilad is the same as here if you just identify as one orbit.
Yes, sure. I mean, it's included here, yes.
Can you say, I'm sorry to ask this.
No problem.
Are you saying 9, like the number 9, or are you saying something else? Because I see K, different states.
Did I say 9? Yeah. Oh, sorry. No, it's there K. Oh, sorry, but I don't know why I say 9. So it's the K. So for the case of the K times K, then we have the K classes.
Great.
Okay. Everything is clear. Thanks. Okay, and obviously this. So for the case of the bipartite or the matrix, we can. So our goal is we like to do the similar procedure for the tensors. But the question is how we can draw these closures, and probably But one idea you can look is of course here already somehow described answers, but one idea is look. Of course, we can always define the separable state as a pure tensor. And there is famous duality in complex projective space, namely the duality between the space of the dimension of the singular variety and its dual variety, which has a codimension 1 in this case. So there is duality here, and the largest the subvariety, and which is characterized by determinant, because this set is nothing but the rank is equal to or less than k minus 1. Okay, so this is, and all somehow intermediate closures are characterized as somehow the singularity of the dual variety. So my approach is essentially we are going to define this first the duality and try to look at the singularities to somehow draw the same pictures for the case of the tensors. Is everything clear? Okay, so I think we already saw, so I don't repeat. So the first question is how about the 2 by 2 by 2 case, or we call 3 cubic case? And as David pointed out, when the people in quantum information got interested in the multipartite entanglement, basically what surprised us first was if you look at the multipartite case, there are several ways to be the maximally entangled in some sense. Okay. Of course, I mean, if you look at the mathematical literature, of course, for example, the same remark can be found in this textbook by the Gelfand, Kaplanov, Zelensky about the discriminant, resultant, and the multidimensional determinant. And if you look at the last page, they just kind of write down the result for the case of the 2 by 2 by 2 without much explanation. But somehow the thesis found the meaning of this characterization. And this is what we like to do in more. And that story of the today. So now I like to define duality. And usually this is a slide I kill all attention of physicists. But probably I don't have to even explain to you here. So the idea is somehow that we like to define the similar correspondence between the Segre variety and the determinant. And this is how Gelfand and his collaborators define the duality. Okay, so we consider the set X, and for our case, we are going to define X to be the Segre variety, namely the set of the completely separable states. And the dual variety is defined in such manner that this state is included in the dual variety if there exists a point on the Segre variety where somehow this tangent, the hyperplane somehow tangent to this variety X. Well, usually somehow I try to explain what is the meaning of the hyperplane. This is kind of the set of the orthogonal state to the psi in this picture, but probably you are much familiar with this definition. So we consider the multilinear form this way, and the condition I just phrased here of the dual variety is nothing but the set of the linear form, and the first derivative for every x should have at least one non-zero solution, okay, to have the tangent point. And the condition for this existence is nothing but the condition for the dual variety. And if this is codimension 1, and this happens only when we have specific somehow format, roughly speaking, somehow the subsystem should be small, reasonably smaller than the rest of the space. Then somehow we can define the hypersurface here, and this is the definition of the hyperdeterminant in general. Any question in this slide? Is this okay? Okay, good. Okay, so, and there are a lot of things known about hyperdeterminant. So for the 2 by 2 case, it's just standard determinant. And Kelly found in 19th century, this is Kelly's hyperdeterminant of degree 4. And as I briefly mentioned, these quantities are good to characterize entanglement in the sense that this absolute value somehow characterizes the amount of genuine multipartite component in entanglement. On the other hand, this n-qubit hyperdeterminant is very complicated object in the sense that the degree is known to be growing up very fastly. So even 4-qubit is degree 24 and blah, blah, blah. And if I know correctly, there are still activities on to characterize this hyperdeterminant in terms of the decomposed monomial and how many terms you have. But this is what we like to do. Essentially, we like to somehow define hyperdeterminant, and conceptually, we like to look at the singularity of this hyperdeterminant because these are somehow they gives us different entangled states. So this is my interpretation of the known results, but you might somehow figure out the better. Let's look at more carefully. So the whole space is the dimension 7 because we have 3 qubits, namely 2 by 2 by 2. And there is first somehow closed variety is given by the dual variety. And definition is hyperdeterminant itself. And the outside of this state, outside of this dual variety, is the most generic orbit of dimension 7. And you can find one example, and this is so-called the GHZ state. So this is the GHZ class is mathematically defined as the whole state, and the subtract the dual variety here. And the next is the, as I said, first somehow we consider the Segre variety in the middle, and we took the duality. And there are somehow intermediate varieties, 3 ways, because naturally you realize that there are somehow 3 ways to consider the Segre embedding of the CP1 times CP3, okay? Because we have the 3 qubits, so you can somehow combine 2 in 3 ways. So the W class is essentially outside of the combinations of the 3 possible Segre embedding. And this is somehow by definition, you can see that this class is tripartite entangled, but it's separated from GHZ in the sense that the dimension of the orbit is the 6, and typically we took this W state as the one representative in this region. And as I mentioned, there somehow 3 dimensions for Segre varieties by CP1 times CP3 here. And in the union, the dimension 3 of the Segre variety in terms of CP1 times CP1 times CP1 is the smallest closed variety in this setting. And in principle, we got the old characterization of the orbit, in this way. And conceptually somehow also I characterize that these somehow, the Segre varieties can be said as the singularity of the dual variety, in the sense that if somehow the hyperplane is tangent to the 2 points at the completely separate set, namely on the x, then it becomes kind of the node kinds of the singularity. And this is the characterization for this 3 CP1 times CP3. And when somehow the tangent hyperplane somehow touches this way, namely the second derivative is also 0, then it becomes as a cusp, and the actual CP1 times CP1 times CP1 is nothing but the cusp singularity of the dual variety. So I kind of guess you may have the better tools to somehow do these things, but that's the program I somehow started looking at in the past. And I have a few more somehow the example along this line. Is there any question up to here?
Can you be a little more specific about what cusped node means exactly?
Okay, so this is singularity. So if we have more than one solution.
Okay, but axis of high dimensional, I don't know how to say it. In fact, axis of high dimensional space, right? It's not like a curve.
Right.
So what is cusped node?
So the dual variety is these tangent hyperplanes. That is, the hyperplane intersect x is singular. Okay? And there's 2 ways you could have singularity that's not an A1 singularity. Either you have A2 or greater singularity, which is cusp, or it's singular at more than 1 point. That's node. The hyperplane section H intersect x is singular. So it could either have one, generically it'll be a single A1 singularity.
Yes.
Okay, after that there's 2 choices. It could either be an A2 or bigger singularity, which is called cusp.
So precisely what I'm asking here is, do you ever see bigger?
What?
In this example, do you ever see bigger than A2?
You of course will see bigger than A2 in general.
Those two. What's the next worst thing that could happen?
Yeah, I mean, if you're on the Segre, it's going to be much worse than A2 because it's
Okay.
yeah, but.
Thank you for the clarification. Okay. So this is what I got for the little bit bigger case. For example, we consider 2 by 2 by 4 case. And we see the same structure in the middle part. So this part is same as the 3 cubic case, but now this somehow the third, the dimension is 4, so we have more orbits. And the idea is we can somehow consider there somehow duality between the varieties, and actually the dual variety of the total space, namely the subvariety of codimension 1 is the dual to the B3 in this case, biseparable between, I think this is B3 is CP3 times CP3, and the dual is somehow the closed variety of codimension 1. And similarly, the dual variety of the completely separable state is given to the intermediate the orbits. But in a nutshell, we can somehow characterize every orbit in terms of the algebraic varieties. And in this case, I think we have 9. Sorry, so probably this is the reason, in my mind, always 9 is in my mind. So we have the 9 different entangled classes here. And as already somehow mentioned, in this case, we still have the finite classes. But it is known that if you consider more parties like the 4 qubit OR, then in general we have infinitely many causes, in the sense that we may have the finitely many closed varieties, but in between we have infinitely many orbits in general. And if you like to somehow classify, the algebraically, so these 9 classes, in principle, you can use a lot of somehow the good invariants, and we call entanglement measures. For example, for generic class, of course, we can just check the essential local rank. So this is a little bit similar to, as David said, for given total state, you can easily calculate the reduced operator for the ice particle by tracing out the rest. And you can easily calculate the ranks, and if somehow rank is 2 and 2 and 4, full in the whole the subspace, then you can easily say this is somehow the generic orbit. And if you get 2 and 2 and 3, as we saw, you have the 2 possibilities. And this is essentially somehow distinguished by the corresponding determinant. So for this case, we have the determinant of the 2 by 2 by 3 form. And when you get the set of the local ranks by 2 and 2 and 2, then essentially this is what we saw. You can use the hyperdeterminant and this distinguish GHZ and the W class. And if you have the much smaller, then they are somehow not the genuinely tripartite entangled. So if you have the these 3 possibilities essentially by separable in the sense that the only somehow 2 parties are entangled, and if you have the all 1, it corresponds to completely separable states. And usually somehow the physicists somehow they draw the diagram, something like that. So for the 3 qubit case, we have only 3 layers. So the surprising fact is, although somehow if you draw this diagram like this onion shape, GHZ state is the generic and the most outer, but this doesn't guarantee actually we can convert GHZ state into the W state. So if you try to do that, actually the successful probability is vanishing. So the only you can do is actually you can transform GHZ into the lower classes, and similar happen to the W. So the difference compared to the bipartite case is the hierarchy of the multipartite entanglement is not totally ordered in general if you consider the invertible transformations. Or phrased differently, in order to characterize multipartite entanglement, you need several measures. Okay. For the case of the bipartite case, you can only look at the rank and it somehow determines the conversion. But here, of course, the dimension is one thing, but for example, as I somehow come to later, tensor rank is also the one of the entanglement measure in the sense that the tensor rank is also decreasing. That is why you cannot go to GHZ to W. You cannot increase number of terms here. Okay. So there are a lot of constraints, and that is why in later physicists usually prefer to this diagram. And for the case of the 2 by 2 by 4, this is the whole picture. So we have unique class. This is generic orbit, and we can safely say this is maximally entangled because from this state you can go everywhere. But in general, we don't have the unique class in multipartite entanglement.
Can you go, is it with certainty?
From here to the bottom?
Like, can you go from the top to any one below with 100% success?
I doubt it. Usually not. Yes. You can easily see, so this state is nothing but somehow the 2 EPR there. And your question is whether we can create an arbitrary state from this state, and generally no. Okay, so as I briefly mentioned, we could somehow continue on this process. So for the case of the whole qubit, this is a little bit complicated, but I think it's known as the Schral-Fies method to construct the determinant of the 2 by 2 by 2 by 2 using the smaller format of the determinant, using this way. And as briefly we somehow saw, whole qubit case, we have infinitely many SLOCC orbits. But the generic class is always characterized by the non-zero hyperdeterminant. Okay, and naturally we have 4 parameters, and here, and as far as the van der Monde determinant is not 0, then you could say this is generic form in entanglement. And the one notice is in general GHZ nor W's are generic type entanglement, so they are a little bit limited, although they are very famous and easily write down, but the zoo of the entanglement is a little bit intricate. And I think I'm a little bit behind my schedule, but briefly mention one open question. So for now, when somehow the 2 speakers talked, we are usually talking, or they are talking about so-called single copy classification, meaning that you have a state, just one copy, and you are asking what you can do. And in the context of the quantum information, also we are interested in the asymptotic case in the sense that we have infinitely many identical copies, and you could ask whether somehow you can somehow do this certain somehow transformation. And for the case of the bipartite case, the question is, suppose the psi prime is given by this non-maximally entangled state, but you have m copies. And the question is how much you can get the maximally entangled state with equally balanced. And the question is how many n copies you can get. And it is known that we can make this transformation reversible when somehow this n is given by the m times the entropy of the reduced operator here. And this is very important result in quantum information. But to my knowledge, we don't have any geometric understanding what's going on here. So naturally, we have the m copies, so we have, we could imagine this is kind of the geometry on the symmetric subspace, and we could think we could use a lot of embedding like the Veronese embedding. But the difficulty is usually I don't see the entropy function in algebraic geometry. Maybe I'm wrong, but that is why somehow it's known in the context of the information theory. But if we consider asymptotic settings, I don't have any somehow geometric understanding. And furthermore, in principle, we like to do same characterization for multipartite setting. Because this characterization tells us if you consider asymptotic situation, essentially there is only one kind of the entanglement. You can count the amount of entanglement by counting as the number of the EPR states. But the question is whether we can do same things in multipartite setting. So we like to somehow compare the arbitrary state by decomposing into the representative states, but it is not known whether we can do such conversion in a reversible sense. So the people somehow call this set possible kind of the unit of the multipartite entanglement set as a minimally reversible entanglement generating set, the MREX, in the sense that this transformation can be done in a reversible sense. I think the mathematical difficulty is the LOCC is a little bit more complicated than SLOCC. because we have to care about the successful probability. Okay, certainly LOCC includes local unitary operations, but we can do more than that. So I think that's one little bit difficulties, but if you have any idea to the multipartite settings, that's big still open question in your community. So this is the first part of my talk. Any questions so far?
Yeah, I mean, how to say, suppose I relax that and just allowed SLOCC here. Would you then have an answer to
Oh
the
yeah,
question?
well that's trivial. Because somehow in Bipartite case, it is trivial, but because for each copy, you can transform to the maximally entangled state with same rank, right?
Not this question, this question.
Okay, so of course, the first question is if we consider the m copies, then it corresponds to we have infinitely many orbits, right? So in principle, if you somehow pick up the all representative states, it's doable. But even we don't have characterization of every the orbits in my knowledge. But no, of course, we have the condition of the symmetry, namely we have the identical m copies. So this should reduce the number of possible orbits, but I'm not sure whether somehow still we can get the finitely many orbits.
Maybe ask this question one more time. So if I convinced you that you can't do this with SLOCC with finitely many generators, would you then also know that you can't do it with LOCC with finitely many generators?
This is another question. If you are addressing the SLOCC, this is different question. But as I said, if you somehow try to connect by SLOCC, then I think only answer is you like to pick up what's the possible somehow the orbit we can get by considering m copies. And the only question is whether this is finite or infinite, which I don't know.
Isn't it because it can go from the GHZ to the bell state.
Right.
So why actually I need, can't we just...
Oh yeah, because originally we want this to be the reversible. So we don't want, of course GHZ is more expensive unit, okay?
Right.
So because if you have a lot of bell state, you can create a GHZ state, but there is...
And now how long, I mean, I'm trying just to understand the question. How long, how many qubits, what's the limit? Like here you had 3 qubits and 2 qubits. What about states from 4 qubits? How do we know?
Suppose this is 3 qubit state.
Oh, okay.
Okay, let's say.
That's funny.
Yes.
Okay.
Yeah, then somehow, I didn't write down the product state because this is free resource. Okay. So just let you know there are some open questions in this context. And in remaining time, I'm going to briefly mention the second part, namely the complexity. And as you already sense, somehow, in quantum computation, usually we have the similar diagram of the Boolean network, but instead we prepare the state and we apply gate operations, and usually these gate actions are chosen from the SU2 acting on the only 1 qubit or SU4 acting on the 2 lines here. And naturally, you can see that if you apply the SU2, it doesn't change the entanglement because this is local unitary. So the amount of the entanglement is modified whenever you apply 2-qubit gate or SU4. And if you consider the quantum computation as the quantum circuit, namely starting from product state, you generate entanglement, and in some moment you like to get the output state, and you are going to measure and read out certain somehow answers. So the complexity of the quantum computation can be phrased as the complexity of the state you generated here. Namely, somehow complexity of the quantum computation is reflected in the complexity of the entanglement. So if you somehow characterize the complexity of the entanglement, this has the implication to the quantum computation or limitation of the quantum computation. And just for illustration, in principle, we have a lot of possibility in this circuit diagram, but in the past, people looking at the very simple 2-qubit gate called the control Z gate, given by this form, meaning that you somehow pick up the 2 qubit and you provide only minus sign only when you have the 1 at the both registers. Otherwise, it's just the standard things. So this is similar to the XOR any logical operation, but in quantum case, of course, we can have the minus sign here. And this is the valid the unitary operation here. And then somehow this essentially if you have the control phase gate, all gates are commuting because this is in the Z basis. So it means that whenever you apply a lot of the control phase here, you don't have to be worried about orders because they are commuting. So that's the big simplification of the example. And that is why we don't line this line anymore, but we just mention the connection, which qubits are connected by the control phase gate. So this diagram only somehow explain which qubits are connected. So in this example, we have 2 lines or 2 qubits, and they are connected by CZ. And this represents nothing but the bell-type machinary entangled state. If we somehow initialize state into the plus state, which is just this shorter notation for the 0 plus 1 state, you can just easily calculate, starting from the plus and the plus state, and if you apply this 2 qubit gate, then in the end you get essentially this state. And if you have the 3 qubit and act on the neighbors, then you get to the GHZ state. And you can do a lot of things. And for example, if you have this chain of the 4 qubit and acting on the neighbors, it somehow has the tensor of this form. Well, I have a little bit subscript which specifies the basis, but you can essentially see this is the kind of the long tensor. And this is a little bit different from GHZ because you can see the tensor rank is bigger than GHZ state, for example. And it is called cluster state. And you can ask complexity of this entangled state. And you can ask whether somehow we can do quantum computation using such the entangled state. And there's long story, but we define graph state in this manner. Namely, somehow the given graph, you somehow, according to this pattern of the edges, you apply control phase gate. And there are a lot of varieties, and this covers a lot of important classes. Like the GHZ state is generally corresponding to this tree-type graph. And if you consider this the 7 qubit thing, then it has some intrinsic error correction property. And this is just 2-dimensional grid, and it's called the 2D cluster state. And although somehow I don't explain in detail, surprising fact is if you have certain entangled state, like 2D cluster state, by doing just LOCC is enough for you to simulate any quantum computation. Place differently, so this is usually people call universal resource for quantum computation, in the sense that if you are provided to this entangled state, all you have to do is LOCC as we saw in the first part. Basically, you are starting to do the measurement and doing a lot of the local transformation, and you can simulate any quantum computation. Okay, so and if you have some very dumb resource, obviously if you have the no-entangled state, you cannot do any quantum computation. So apparently this somehow gives you some idea about the power of the quantum computation. So this is roughly what I said. The complexity of the state is somehow the representation of the complexity of the quantum computation. And we consider the set of the psi is universal for this measurement-based quantum computation if you can produce any state, because in quantum computation you are supposed to produce any state. So if you can produce any state, you call the set of state as a universal. And there are a little bit few details. One thing is compared to the first part. Here you may somehow change the size of the particles. Okay, so usually you are starting from the big resource and you are starting to do the LOCC, and you are happy if you could prepare any state of the target in the lowercase n. And usually you want this overhead to be polynomial large. So if this capital N is at most polynomial in the target size, then you consider this original state is good one. Okay. And essentially, this entanglement measure somehow tells you whether somehow this given state passes the the test holds the universality or not. Because the entanglement is the monotonically decreasing under LOCC, so in order to be the universal resource, it should have the high entanglement. Because this value is only decreasing, so if this is limited, there's no chance to create the entanglement with higher value. So that gives us the necessary condition for universal resources. And one thing I like to highlight is we call entanglement width, which is related to the certain graph invariant. And one more thing I should point out here is we have the Schmidt measure, but actually this is nothing but the logarithmic of the tensor rank. So the tensor rank is also another interesting thing. But of course, physicists are a little bit sloppy to check what's known, so we have another name, unfortunately. Entanglement width is shortly said, this is nothing but the rank width, if you know the graph theory. And we can somehow say that this is essentially the good entanglement measure in the sense that this is no increasing. And the fact is if you calculate this quantity for the 2D cluster set, this diverges. Okay, so it's unbounded. I skip this slide. So the first theorem is any set of the graph set whose entanglement width is bounded for the number of qubit n cannot be universal because there are some state you cannot create. And for example, the whole one-dimensional clusters, this one-dimensional chain is limited and it is not universal because if you calculate the tree width, then this is just one. Interestingly, if you look at the tensor rank, this one-dimensional cluster set has still big the tensor rank, but this doesn't somehow allow us to eliminate this 1D cluster state. So my point is in order to somehow characterize as a resource of the quantum computation, you need more than one measures. Or there might be the measures, but we don't know what is. For example, if you look at the only tensor rank, you cannot tell whether this is universal or not. And there are a lot of somehow the similar graph sets which are not universal, like the GHZ states. Usually we consider this is highly entangled, but actually this is nothing but tree, so it has limited complexity, so it's not universal. And there are a lot of more examples. And this is somehow also the coincide with another idea of the classical simulation of the quantum circuit itself. Because somehow in this argument, I attribute the complexity of the quantum computation to the entanglement. But you could somehow just argue the quantum computation is nothing but the contraction of the tensor in certain orders. And this is, one might do the similar argument. And for example, you can find the two articles by the computer scientists. For example, this first paper considers the quantum circuit, so it's a little bit maybe too small to read, but the quantum circuit as a tensor network, and they show that the tree width of this tensor is limited. You have a chance to simulate a whole circuit by classical method. And this is somehow coincide with our intuition. That is, this cannot be universal. Okay, and there are several arguments along this line. On the other hand, there are several somehow known classes for universal resources. And at least somehow they have unbounded entanglement. And in particular, for example, we can say that all regular the tilings in 2Ds are universal. So not only somehow square lattice, you can do universal computation using different geometry. And as I already somehow briefly implied, we have also the generalization of the graph state using the tensor network state. And for example, the David Gross had the important contribution in this direction. And the tensor network states are a little bit popular in physics nowadays. But I realized, so they essentially, in the graph set, we consider the special 2-qubit gate called control phase gate. But you don't have to consider this gate. And in general, we somehow consider the state generated by the lot of tensors. And I realized that there was another workshop in the Simons Institute in this April about the tensor network and simulations. And finally, the audience and the participants are completely different from this community, and this is rather a bunch of the physicists, and we see maybe 1 or 2 computer scientists. But if you are interested, you can look at the videos of this workshop. But anyhow, on the second part, the conclusion was somehow we can characterize the complexity of the quantum computation using measure of the entanglement. And to be universal, the entanglement should be macroscopic, in the sense that it should somehow the scale, essentially proportional to the system size. And for certain measures, like for example, tensor rank, we can even say that this characterization is good in the sense that if this entanglement is only logarithmic scaling, then you can say actually this resource is not only not universal, but also there is a way for you to somehow simulate efficient research computation. So that we can even say this is in P. So this is a summary of my talk. So in the first part, I somehow gave my interpretation of the classification of the entanglement in terms of the algebraic geometry. And the 2 big questions, obviously, the first thing is we like to complete this program, and I think, and also from the physicist perspective, also we like to understand the implication of the all, the all somehow variety of the orbits, because somehow the difference of the orbit characterizes how somehow the correlation can be shared in the multipartite setting. And as well as it was mentioned once, the difference to the classical correlation is in entanglement, we have non-trivial constraint, meaning that the entanglement cannot be shared in an arbitrary sense. So this is called monogamy of entanglement, and essentially we like to interpret this classification as a physical constraint. For example, somehow the fact somehow the 2-party only somehow, if somehow you guarantee that the Alice and Bob share the EPR state, it only somehow guarantees that the Alice and Bob has a perfect correlation, and this is exactly the basis of the security in quantum cryptography, okay? Because there is no way somehow the Alice nor Bob is somehow connected to the third person in this setting. So there are a lot of somehow the application using such constraint. And as I briefly mentioned, the asymptotic case is largely open. On the second part, of course, we like to somehow find necessary and sufficient condition, even for graph state, to be universal, which is unknown. And also the other complementary questions, we start looking at the classes of the tensor network, which can be still handled efficiently in classical manner, so that actually, we can somehow use in the variational answers in the many-body system, for example, in physics. Thank you very much for your attention.
Questions?
What's a small example of a tensor network for which this question is open?
Well, actually, the question is, actually this state has own name. So this is extension of the graph state. We call matrix product state. So for each somehow the tensor, basically you could imagine these circles correspond to qubit, and we determined how they are connected. And this system is known to somehow convenient to describe one-dimensional interaction system like the David, for example, talks about, because this naturally somehow encodes the information about the two-body interaction. Okay, and if you have the higher dimensional state, then you might expect you need a more complicated description for the entanglement. So this is, compared to this one-dimensional description, this has more long-range interaction. So if you expect the system is more, correlated, you should somehow. But the nice thing about this is somehow so-called the mirror, in the sense that somehow it represents a lot of physical properties you expect. I don't somehow explain in detail. And on the other hand, somehow there is good way to somehow keep contracting things. And because if you write down the tensors naively, you may not be able to calculate any quantities. So in physics application, you would like to find the tensor network which are efficiently computable. So we have just those, but we expect to somehow expand more.
Yes. Yeah, so I think much of what you said at the beginning was only for the pure state.
Yes.
What happens, I mean, do these techniques tell you anything about the mixed state case?
That's the thing. So in the beginning, I somehow said that I'm going to learn from you in the sense that we have the very nice correspondence between the geometry of pure state and the algebraic geometry, but this breaks down immediately if you consider the mixed states. In principle, I think there are some ways to do that, as we already see. So if you have the 2-qubit mixed state, essentially this corresponds to the 4 tensors you have, So even 4 tensors, of course, even if you do the SLOCC classification, we have infinite orbits. So in principle, you can do, but it's much complicated immediately.
Any other questions? All right. If not, let's thank those.
Thank you very much.